So we will get underway with actually the final lecture of this program. We're very pleased to have the exciting conclusion to Daisuke's lectures on tensor networks and the tensor renormalization group. Daisuke, over to you.
Okay, thank you. And in yesterday's talk, I talked about how to handle gauge fields in the TRG method, and I also talked two higher dimensional TRG algorithms called higher order TRG and anisotropic TRG methods. Today, I'd like to talk about another higher dimensional algorithm called triad TRG method. And after which I will be explaining how to handle fermions in TRG method. And then I will be introducing an application of TRG to quantum range calculus, which is a model of quantum gravity theory. Finally, I summarize. And the renormalization steps of higher order TRG is made of two steps, making projectors from two tensors. This is the first step. And the second step is to make a renormalized tensor by contracting two tensors with the obtained projectors. And however, the cost of HOTRG is high, and the cost of the ATRG improves the cost of HOTRG. And the reason why ATRG's cost is high is that the tensor is rank 2D tensor in D dimension, and the cost of contracting two rank 2D tensors is high for large D. So we need to reconsider a tensor network theory at a fundamental level to reduce the computational cost. And as you know, proton is not a fundamental building block of nature. A proton is made of 3 quarks. The quarks are fundamental building blocks. Similarly, rank 6 tensor in 3 dimensions is not a fundamental building block of tensor network theory, because rank 6 tensor is expressed as a tensor network of 4 rank 3 tensors. In this talk, this structure is called triads in this talk. And so these dotted lines are internal indices. So taking the contraction of these internal indices, this network coincides with the rank 6, this rank 6 tensor by taking the contraction of these dotted lines. So rank 6 tensor is not a fundamental building block, and this structure is fundamental building blocks. So actually, the tensor which is obtained from a lattice theory takes this form, because as I already mentioned several times in this lecture, the rank 6 tensor in 3 dimensions, rank 6 tensor in 3 dimensions is made of 6 W's. These W's come from the hopping terms of 6 links. So this A is a field variables, and integrating field variables, and rank 6 tensor is obtained like this. And normally we this rank 6 tensor is used to tensor renormalization group calculations after taking this summation. However, and this form is called periodic decomposition of a tensor. And this periodic decomposition of a tensor can be expressed as a tensor network of rank 3 tensors by identifying rank 3 tensors A, B, C, D like this. Periodic decomposition is simply expressed as a tensor network of rank 3 tensors. So the tensor network obtained from a lattice theory is initially expressed as a tensor network of rank 3 tensors without any approximation. Okay, so I proposed the tensor renormalization group method on this tensor network made only of rank 3 tensors. And the computational cost of TRG is naturally reduced because the computational cost of taking the contraction for rank 3 tensors is not high. So the cost of contracting 2 rank 3 tensors is basically proportional to d to the 5th. So the computational cost of triad tensor renormalization group method that I called is not high. If we define a renormalization group method on this tensor network, triad tensor network, okay? So, and the higher order, and the higher order TRG like renormalization scheme is if the higher order TRG is applied to this network, the projector is made from 2 diagonalization of 2 tensors, and M, which is made of 2 tensors, is expressed as this diagram in triad representation. And this diagram can be expressed as this form. And M dagger is a mirror image of M. So the M dagger, which is used to make a projector, is expressed by this diagram. And all the tensors in this diagram are rank 6 tensors, rank 3 tensors. So taking the contraction of some internal links, we obtain this diagram exactly from this diagram due to the 5th cost. And taking the contraction in this diagram, dagger is obtained due to the 6th cost exactly. And the cost of diagonalizing dagger is proportional to d to the 6th because dagger is d squared by d squared matrix. So this means that the projector U can be exactly prepared at the d to the 6th cost in any dimensions. This is completely different from the
So it looks like the connection has dropped. Let's wait a minute to see if it recovers.
Okay.
We can hear you again now. Yes.
Okay. So, this is completely different from the HOTRG case. in HOTRG, the cost of making projector is proportional to D to 2D plus 2. On the other hand, in the triad TRG case, the cost of making projectors does not depend on the dimensionality, but D to the 6 in any dimension. And this cost can be reduced up to D to the 5th by using some numerical techniques called randomized SVD technique. And once the projectors are obtained, the two triads can be renormalized into a single triad. And in this step, we need to take some contractions, and it takes D to the D plus 3 cost. So the main computational cost of our triad TRG method is proportional to D to D plus 3. Okay, so I'll skip this page. So and this table summarizes the theoretical computational cost for several TRG algorithms, and the original TRG method is formulated only on 2 dimensions. The cost of the TRG method is D to the 5th, and the cost of HOTRG is D to the whole D minus 1, which is D to the 7th for 2 dimensions, and D to the 15th for 4 dimensions. So the cost of HOTRG is high. And the cost of HOTRG is proportional to D to the 2D plus 1. On the other hand, the cost of triad TRG is reduced to D to D plus 3, and D to the 5th for 2 dimensions, D to the 6th for 3 dimensions, and D to the 7th for 4 dimensions.
So a quick question about that last line. Wouldn't you still have the D to the 6 from the projection step for triad TRG, even in 2 dimensions? I think you said that was independent of dimensionality.
So randomized SVD techniques.
Oh, that's right. You can reduce that. Sorry.
The cost. Okay. So, and in this contraction step, randomized SVD techniques is needed to reduce the cost. Okay. So this is a theoretical computational cost, and we tested our method in three-dimensional Ising model to check this theoretical cost and accuracy of, and check the accuracy of results. And this figure shows the numerical test results in three-dimensional Ising model at critical temperature. X-axis denotes D-cut, and Y-axis is real computational time. So theoretical D-dependence is properly reproduced in actual computations, as you can see this figure. So, and this figure shows the D-dependence of free energy, and the maximal D-cut, the maximal values of D-cut depends on the renormalization scheme, because the cost depends strongly on D. So the cost of HOTRG is high, and D is 12 for HOTRG, and we can take D equals 56 for triad TRG method, because the cost of triad TRG is not high. And all the computation in this in this figure were completed within a few hours using laptop computers. And as can be seen in this figure, the triad TRG method shows good convergence as D increases. And this dotted line is the extrapolated value, which is obtained from the extrapolation of triad TRG result to the infinite D-cut limit. And also the extrapolated values are obtained from HOTRG results and ATRG results. They are consistent with the extrapolated values obtained from triad TRG. Okay, and this figure shows free. In this figure, free energy is plotted against real computational time. So, we can say that the other methods need much more time to approach a converged value around -3.509, and the triad TRG shows a good convergence within a few hours computation. Okay, so actually in 3 dimensions, at least in 3 dimensions, the triad TRG method is very effective. Okay, so and we formulated the triad TRG method using this kind of decomposed representation of a tensor, rank 6 tensor in 3 dimensions. However, there are many kinds of decomposed representations for a rank 6 tensor. And actually, you can mix the rank 4 tensor to decompose the rank 6 tensor. And the accuracy depends on the type of decomposed representations. Okay, so and this figure, this is a schematic picture of Hall error at a fixed time. And x-axis is the number of internal links. The 2D rank tensor, rank 6 tensor, 2D rank tensor does not have internal links. And if we apply HOTRG to this 2D rank tensor directly, we obtain very accurate results for fixed D-cut. However, we cannot take large D-cut because the cost of HOTRG depends strongly on D-cut, so we cannot take large D-cut. So the accuracy of the results is reduced for HOTRG. On the other hand, if we use triad TRG method in 4-dimensional theory, there are 5 internal links in a triad representation of rank 8 tensors. And so an extra decomposition is needed to make a renormalized triad representation, and the accuracy of results is reduced due to such a extra decomposition. So the accuracy of results is also reduced for triad TRG method in 4 dimensions. And I guess that the best decomposed representation is 1 between rank 2D tensor and triad representations. So, and to find the best, I'm not sure what the best representation is for D is, and how to find the best representation. So these are still open questions. Okay. And okay, I'll skip talking about second renormalization group method, which is an improved method of TRG. And okay, next I will be explaining how to handle fermions in TRG method. And the TRG method for fermions has already been proposed by Gu and the others, and which is called the Grassmann TRG method. And the Grassmann TRG method, the GTRG method, has already been used to study Schwinger model and Gross-Nouveau model. But this original method is a bit complicated method, so we reformulated the Grassmann TRG method in this paper, and we derived general tensor network representation for local lattice fermion, such as Wilson, staggered, and domain wall fermions. And in this lecture, I will be explaining how to derive the general form of tensor network in local lattice fermion action. And so, firstly, let's define Grassmann tensor, which is used in the Grassmann TRG method. And as I mentioned several times, the tensor index is basically the field variable. And also in the case of also in case of fermions, the tensor index is the Grassmann number so the Grassmann tensor is defined by this, and yet n one component Grassmann numbers satisfying the standard anti-commuting relation, and these I1 to In are the occupation numbers that takes 0 or 1. And this T is a regular tensor called component or coefficient tensor. And this tensor is a function of the parameter of fermion theory. So this is a definition of Grassmann tensor, and diagrammatically, the Grassmann tensor is expressed by this diagram, and these indices are assigned to these external lines. Okay, so this is a formal definition of Grassmann tensor, and as I explained later, this Grassmann tensor appears from the local fermion action. Okay, so and the contraction, a contraction among Grassmann tensors is defined by this, and this is a contraction between a Grassmann tensor A and Grassmann tensor B, and the contraction is taken from eta 1 of A and theta 1 of B. And the Grassmann contraction is defined by the normal Grassmann integrals with this weight. Okay. And diagrammatically, this contraction is expressed by this diagram. And Grassmann contraction has direction. So the arrow is used here because the Grassmann contraction has the direction. It's taken from it's taken from theta to theta bar, so it has a direction. And so numerical methods such as the SVD and diagonalization can be translated into the language of Grassmann tensors with these two definitions of the definitions of Grassmann tensor and the definitions of Grassmann contractions. I don't explain this point in detail, but it's easy to find the SVD of a Grassmann tensor by which the Grassmann tensor is decomposed into two Grassmann tensors. So we can decompose a Grassmann tensor into two Grassmann tensors, the Grassmann SVD techniques. Okay. So with these definitions, we found corresponding rule between a regular TRG and Grassmann TRG. In the normal TRG, tensor is given by a regular tensor, and the contraction is the summation of the index. And the tensor network is defined as a product of n tensors whose indices are all contracted. This is the definition of tensor network for regular tensor. And in TRG method, the renormalization is carried out with the singular value decomposition of tensors. Okay. On the other hand, in the Grassmann TRG methods, the fundamental tensor is given by Grassmann tensor, defined by this, and the contraction of two Grassmann tensors is given by Grassmann integrals with this weight. And the Grassmann tensor network is defined by a product of n Grassmann tensors whose indices are all contracted under this rule. Okay. So under renormalization of Grassmann tensor network is carried out using the Grassmann SVDs. Okay. So once the corresponding rule is found, you can translate ATRG or HOTRG into a Grassmann ATRG or Grassmann HOTRG using this corresponding rule. Okay. So, and here I'd like to explain how to derive the Grassmann tensor network representation of partition function in D-dimensional local Fermion action.
Daisuke, one question.
Okay. Hi.
On the previous slide, this Grassmann SVD is the same as SVD, right? Is there a difference?
It's not the same, but in the Grassmann SVD, the component tensor is decomposed by the normal SVD, okay, in the Grassmann SVD, but the extra decomposition for Grassmann variables here is needed in this Grassmann SVD. Component field is decomposed by the normal regular SVD. And extra decomposition for Grassmann numbers is needed in the Grassmann SVDs.
Okay, thanks.
Okay.
So I have a raised question. I'm Takihiro. May I ask a question?
Okay.
So in the top left column, so this is 4 rank 4 tensor world. The top right column is the rank m tensor. And is there a relation between the rank top left and top right?
Do you mean what the rank of Grassmann tensor is?
Yes. The left side is the rank 4.
Okay, this the rank corresponds to the number of link. In 2 dimensions of the number of links is 4, so the tensor network is given by the rank 4 tensors. And on the other hand, in the Grassmann tensor, this and so so Grassmann hopping the hopping terms. Sorry, how should I say? How should I say? Basically, each index, each link has n. Each link has m hopping terms in general. So each hopping term is expressed as corresponding to a single index, as I explain later. So the number of this n corresponds to the number of links times the number of degrees of freedom for each link. Okay.
So may I understand that the right side is for n equal 4?
Mm-hmm. No.
No.
Okay. I will explain it. I will explain it later. Okay.
Yes.
So let's consider the dimensional local fermion action defined by this Dirac operator. And I assume that the lattice fermion action has nearest neighbor interaction. And the W, X mu and Y mu, W's on W terms are on W term is on site interaction, and X mu and Y mu terms are nearest neighbor interactions. So the concrete form of X mu and Y mu and W depends on the type of lattice fermion. And so, for a given Dirac operator, we can derive a Grassmann tensor network representation of the Paschen function. And as I explained on the next page, the Paschen function is expressed as a Grassmann tensor network. And firstly, and this A is the index of fermion fields, such as spinor index or gauge index. And so these W, X, Y's are some metrics with respect to the index of the fermion field. And firstly, we perform the SVD of X like this. Here, for simplicity, mu index, the index mu is suppressed here, and the SVD of X is given by this. The UV are unitary matrices, and sigma is singular values. And by using this decomposition, the interaction terms is diagonalized by this, where x, k, and chi bar are defined by this. Okay, so the hopping term, this term, and the partition function is given by a product of this hopping term, which can be expressed as this form by using this diagonalization, and using auxiliary Grassmann numbers. This form can be expressed in this form. Okay, so of course, integrating two Grassmann numbers, eta c and eta bar c, this coincides with the exponential minus sigma eta bar eta. And this expression is applied to x terms and y terms. We obtain this formula, and x hopping the hopping term of x mu is expressed as this form, and the hopping term of y mu is expressed by this form. And these parts are the Grassmann contraction with unappropriate weights. Okay, so, and in the remaining part, the important point here is that all the fermion fields psi n and psi bar n are separated from the other fermion field. So we can integrate fermion fields, local fermion fields psi n and psi bar n, and the Grassmann tensor can be obtained by integrating the fermion fields locally, because all the the local fermion fields are separate from the other fermion fields in this representation. And so the Grassmann tensor is defined by this. And so in this representation, the Grassmann, the rank of Grassmann tensor is 2D in this form, but each Grassmann index is made of K mu plus L mu Grassmann numbers. And this Grassmann index is defined on a link, but each index is made of K mu and L mu one component Grassmann numbers. So this n is not the number of links. Actually, it's the number of links times the number of internal degrees of freedom for each link. The number of internal degrees of freedom, not the number of hopping terms per each link, is K mu plus L mu. And these K mu and L mu are then appears in the basically K mu and L mu are the dimension of X mu and Y mu respectively. Okay. So So we found that the general form of the Grassmann tensor network representation for general local lattice fermion, and the Paschen function of this local lattice fermion is expressed as a Grassmann tensor network with this Grassmann tensor. So once the Grassmann tensor network representation is obtained, you can apply Grassmann TRG method to evaluate the value of the Paschen function given by the Grassmann tensor network. Okay. So this figure shows a chiral condensate which is obtained from the 4-dimensional NJL model at finite density. The calculation is carried out on a supercomputer, and the lattice volume is equals 1024 to the fourth. D cut equals 55. And the x-axis denotes the chemical potential of this model. And this is a schematic picture of the phase diagram of this model in T mu plane, and the calculation is carried out for a line near x-axis, as clearly seen in this figure. This expected phase diagram is can be confirmed by the HOTRG calculation. Okay. In small so in the dense region of almost zero temperature, the chiral condensate, the chiral condensate vanishes for the large values of mu, and actually the numerical computation results show such a behavior. Okay, so we can say computation with the TRG have become possible for 4-dimensional NJL model. Okay. And finally, I'd like to talk about the recent progress, which is an application of TRG to quantum logic calculus. And the logic calculus discretizes the space-time manifold by simplicial decompositions without using coordinates. In 2 dimensions, the space-time is discretized by triangulations. And in 2 dimensions, the continuum action is given only by the cosmological constant terms. And after the discretization, the action is given by the total action of this triangulation, and total area of this triangulation, and each area of a triangle is given by this from these 3 edge lengths of a triangle. And in the logic calculus, edge lengths are dynamical variables, so the path integral measure is given by integration of edge lengths. And so, however, in this model, the average edge length diverges in this model. So a smooth geometry is not obtained from this model because the average edge length is a kind of lattice spacing of this model. However, the effective lattice spacing diverges in this model, so a smooth geometry is not obtained from this model. So this is a result of Euclidean case. The two-dimensional Lorentzian quantum calculus was proposed to overcome this problem. In the Lorentzian case, each triangle is defined on the Minkowski space, and right constructor is assumed at each vertex. And two vertices of a triangle are placed on a past right cone with a proper distance sigma. And the third vertex of the triangle is placed on the future right cone. And these two edges are time-like edges in this case. So the area of a Lorentzian triangle is given by these three edges, two time-like edges, tau 1, tau 2, and one space-like edge, sigma, like this. And in this setup, sigma cannot go to infinity while keeping the area fixed. So they also expected that the average edge length stays finite because sigma cannot go to infinity while keeping the area fixed. Okay, so we can actually perform TRG calculation to verify whether the average edge length is finite or not in this Lorentzian model. And the measure of QRC, the measure, integration measure of QRC is not uniquely determined. So we use the local measure, and this beta is a parameter that defines the measure. And actually here is I in Lorentzian signature, but we can use this Poisson function after the analytic continuation of the edge length. So we used this Poisson function to numerical calculations. Okay, so the tensor of QRC, tensor network home of QRC, can be derived by using the techniques similar to the scalar field theory. And this continuous integration is discretized by a summation using Gauss-Legendre quadrature like this. Then the Poisson function of QRC is approximately given by a tensor network of rank 3 tensors. Because this area is it can be regarded as a rank 3 tensor whose index is tau 1, tau 2, and sigma. So the tensor can be defined on a center of triangle whose index is edge length. So starting from the triangulation and by using this discretization of edge length and regarding area function as a tensor, the Poisson function of quantum range calculus can be expressed as a tensor network of rank 6 tensor on honeycomb lattice. The honeycomb lattice is dual of this triangulation. So, and firstly, the contraction between these two tensors is taken. Then the tensor network on a square lattice is obtained, contracting this link. So once the tensor network on a square lattice is obtained, we can apply the HOTRG method to evaluate the value of partition function. Okay, so this figure shows the expectation value of area obtained from the HOTRG computations. And this model, in this model, the expectation value of area is exactly evaluated, exactly solved. So, and the exact value is given by this, and is denoted by this black line, and obtain the numerical results agree very well with an exact value. And this figure shows the expectation value of edge lengths. And from this figure, the expectation value of edge lengths are finite for several values of beta. So we can verify that smooth geometry is obtained from 2D Lorentzian QRC model because the expectation values of time-like h tau and space-like h sigma are converged. Okay, so okay, so I summarize my talk. Okay, so the TRG method have several advantages, as I said several times. There is no sign problem from the beginning, and there is no statistical errors in the TRG method. And it's easy to compute physical quantity on very extremely large volume lattices. And free energy can be calculated directly by using the TRG method. And no difficulty in handling fermions in TRG method. Of course, scalar fields and gauge fields can be handled in TRG method using some discretization scheme. So, and remaining issues, we have many remaining issues. The computation for 4D gauge theory is the most important issues. I think the random sampling method will be useful for TRG computations of 4D gauge theory. But for the improvement of TRG method would be needed to compute 4D gauge theory. And as I mentioned, there are many kinds of decomposed representations of tensor, and so we have many variants of TRGs in 3D and 4Ds. And it's an open question. So to find the best decomposed representation is an open question, still an open question. And I think the most difficult problem is to compute systems with large internal degrees of freedom, such as large n-gauge series, because the size of tensor is very large for large n-gauge series. So some numerical techniques such as SVD cannot be applied to such a large size tensors. In those cases, we needed to compress our initial tensor by using some numerical techniques. Okay, thank you.
Okay. And thanks also for leaving a few minutes for questions or comments to wrap up the lectures in this program.
Yeah, very interesting. I have about 20 questions, but I won't get to give them all. In your last thing, when you went to the Minkowski space, your area formula is now continued to complex tau. Is that what that area formula is?
Yes.
The original area formula was Heron's formula for the area of the triangle, right? Now this area formula is no longer the Euclidean area formula. Is that correct?
No. The naive analytic continuation from tau to replacing tau to I tau. This definition of area does not reproduce the Euclidean area.
It's A is still the Euclidean area?
This A? This A is
function
not.
A, I mean, I could have to work it out, but the function A is still the Euclidean area for sides sigma tau, or no?
No.
So then when you went back to Minkowski's, when you went back to Minkowski space, you kept the area, sorry, back to Euclidean space, you kept the area in Minkowski space, but the coupling constant in Euclidean space. I mean, that sounds to me sort of strange. In other words, this formula here is Euclidean area, standard area, right?
Yeah.
The formula in the next page is just taking L1, L2, and putting an I in front. Is that correct? I can't do the arithmetic in my head.
This definition of Lorentzian area is completely different from this Euclidean area.
Oh, it is. I see.
And,
okay, and maybe I should.
And actually, in Euclidean case, some triangle inequality is needed to form a
yeah. In fact, that was my next question. Is that the integration over the phase space has the triangle inequality. So as a constraint,
yes.
So does Ambor's calculation keep the triangle inequality in place?
Triangle inequality is needed in Euclidean case, but Lorentzian equality is not needed in Lorentzian case.
Okay.
For given tau and sigma, the area is always created for positive tau and sigma.
I see.
Both cases.
Okay, I guess I have to look at the formulas, but are you going to submit, your slides going to be available? Because I'd like to figure it out, actually. Okay, so I have one other question and then I'll stop, okay? When you were looking at the trivalent approach to higher dimensions, for example, in 3 dimensions, you had one version which seemed to me to kept the symmetries. Are you concerned about keeping the symmetries? I mean, when you have a cubic lattice, it has a symmetry, right? But when you broke it up into these trivalent terms, you're destroying the symmetry. Is that something you're concerned about?
Sorry, what symmetry?
Go back to your trivalent vertices for the cubic lattice. Back
Cubic
to the,
lattice?
yeah, you did 3 dimensions and 4 dimensions. Keep going back. Back.
Okay.
Early in today's lecture.
Right. Not Fermi's, just the original thing. Okay, stop.
Here.
Here. Okay, right. So
symmetry.
to me, the left one on the bottom line is more symmetric than the others.
Yeah, symmetry of the original cubic lattice is completely completely broken after the
Right, so I'm just
position.
asking,
So TRG algorithm breaks the symmetry of the.
but it wasn't true in the original square lattice because it was self-dual.
Yes, original square lattice, cubic lattice, the symmetry is kept at the initial tensor network. But,
Right, but if you apply this to a three-dimensional lattice, right, and you start to look at correlations along the XYZ direction, haven't you broken the symmetry, so you're not going to get those to even be the same? You've broken the cubic symmetry?
The cubic symmetry is broken for finite decut. In the limit of infinite decut.
So you break the symmetry even of the lattice by the 90-degree symmetry. Is that correct?
90 degrees of symmetry is kept on the lattice. Is kept on the lattice, but renormalization schemes breaks the symmetry.
Okay, that's what I'm asking. Is
But
that
the large decut limit of numerical results, the symmetry in the large decut limit, the symmetry is expected to be restored.
has that been tested? I mean, usually in enormous lattice theory, you say that the subgroup. You see, the usual argument is that the subgroup, for example, of a cubic lattice has enough rotational symmetry to protect you from irrelevant operators, and therefore the symmetry, the full symmetry of rotation is gained in the critical behavior, right? But I don't. Is this really true of TRG? I'm just worried about it. I'm ignorant, but I'm just asking. Are you really sure that you get back rotational symmetry when you break the underlying lattice symmetry?
Yes. So the renormalization scheme keeping the rotational symmetry is the best method for renormalization, but actually the symmetry is broken by the renormalization scheme in general. So of course the best renormalization scheme keeps the rotational symmetry, I think, but it's difficult to find find a TRG method keeping the symmetry.
Even the lattice symmetry. I'm not talking about rotational symmetry.
Okay,
so unlike the Wilson renormalization group, you can easily keep the symmetry, and here you have a difficulty. But now the question is, does it hurt you when you go to a critical point? Are you really getting back rotational symmetry?
It's a difficult question, but in the infinity decut limit, such a symmetry is expected to be restored. So it's
Okay, I'll stop questioning, but what really surprises me, suppose you put in coupling constants on the original lattice, intentionally not having the cubic symmetry. I would be very surprised you're going to get rotational symmetry for all values of the parameters, right? So I mean, usually the subgroup of rotations is what protects you to at least have that subgroup. And then when you go to the critical point, as I say, in terms of operator analysis, the full symmetry comes out. I'm just wondering, it seems this issue hasn't been addressed in TRG. It seems to be very important.
Okay.
Okay. Anyway, I'll just ask the question. We can talk later.
Hello. I have very simple questions on page number 75.
75. Yeah.
So what are these circles here in the MMM dagger representation of the tensors? The internal circles that you have in the M and M dagger representation, what does they represent basically? The circles.
Sorry, sorry, could you repeat that again? So what is your question?
I'm asking the circles that you have in the representation of M and M dagger, where you have used x1, x3, x2, and x4.
Mm-hmm.
So what are these internal circles representing basically? So are these the tensors with some virtual indices? Because I'm confused, that is why I'm asking.
Sorry. In MM,
Yes,
so,
B,
yeah.
C, and D. Okay.
Yeah.
So you took dagger of it. Okay, that's clear.
Okay.
I have another question, and that goes on the Grassmann tensor variable, Grassmann TRG. There you have introduced A and B tensors. I'm quite not clear about the introduction of those two tensors and the zeta variable that you have introduced with the B tensor. Could you explain?
Sorry, 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 what's your question? BC tensor?
The Grassmann TRG method.
Grassmann TRG. Okay.
Yes.
Grassmann TRG methods. Okay.
So yeah, here you introduced A and B tensors in the next slide.
Yeah.
Could you explain the introduction of these two tensors and how they are being used in the calculations, and especially the zeta variable that you are using here with B tensor and A as well?
This is a formal definition of Grassmann contraction for two Grassmann tensors. So in the actual computations, for instance, in the case of Grassmann TRG, this Grassmann tensor is decomposed into two Grassmann tensors by using Grassmann SVD. I didn't dismiss technique in detail in this lecture, but anyway, by using Grassmann SVD, the Grassmann tensor is decomposed into two Grassmann tensors. So, in other words, this is a SVD for regular tensors. And in the case of Grassmann TRG, this T is given by Grassmann tensors. And these two S's are also given by Grassmann tensors. So the Grassmann tensor T is decomposed into two Grassmann tensors.
Okay.
These internal links can be contracted by the Grassmann contraction rule. So this denormalized tensor T prime is also given by can be also given by a Grassmann tensor.
Yeah, I understand now. Thank you.
So once the corresponding rule is obtained, you can translate the tensor renormalization group method into a Grassmann tensor renormalization group method, like this. So okay. So
I have one question if there are not others to go first. Not seeing any, I'll charge ahead and ask about that four-dimensional Nambu-Generalisinho study, getting you all the way back to page 101 from the very beginning. Because here you were looking at this confinement transition. So page
Four-dimensional scalar
four-dimensional Nambu-Generalisinho, NJL.
NGL, okay.
101.
NGL is here. Sorry, NGL.
There was very interesting confirmation of that expected first-order transition at large density at approximately zero temperature. And I was wondering if this tensor network method can, if it's possible or practical to look at higher temperatures, or at least non-zero temperatures, to try to search for that critical endpoint in the diagram on the right.
I think it's possible. I think it's possible to
So how does that work?
critical endpoints by using the TRG method. Yeah, so it's very interesting. So, but
So I guess you're always going to
yes,
have this symmetric volume, some number to the fourth power, just from the patterns of contractions that you have to do in the RG blocking steps. So your lattice extent will, it seems hard to get a short temporal extent corresponding to a large temperature in the usual lattice way, at least from my naive first impression.
So but in TRG we can calculate for various we can calculate physical quantity for various parameters, and so I think we can choose a parameter to study critical endpoints from the in the TRG calculation. So I think it's there is no difficulty to study around critical endpoint by using the TRG methods.
All right, so maybe I'll check out that reference you have there to see what they have to say about that.
Can I ask something?
Yes.
Hi, Daisuke. Yeah, nice job. So I just wanted to know, I was trying to play around with finite temperature in 3 dimensions using the triad method, but I still understand it's like related to what David is asking. The triad method basically works that number of core screening step mod 3 should be 0. When you want to do a finite temperature, you don't want that condition, because number of steps mod 3 0 is like a symmetric lattice. So how can, like, has someone tried to do finite temperature using triad method? Because I think it's very dependent on the algorithm you use, whether you can do asymmetric lattices, for example. So do you have something to say about that?
No, so I've never tried to try the TRG method for some finite temperature case. So I'm not sure. So in your experience, the accuracy is reduced for finite temperature case here. Okay. So yeah, I'm not sure about it. So
No. By finite temperature, I don't necessarily mean like what I mean is asymmetric lattice. Let's be more precise. So this is, I think this is the plot you're showing is for some symmetric lattice, like all the 3 directions are the same or something, right? What if one of them is shorter or bigger than the other? So suppose I want to do 1024 by 1024 by 256.
okay.
I don't know of how triad can handle this, right? Because always do multiples of 3. So that was one problem I tried to do and I couldn't. Maybe there are other methods work. I definitely know that the HOTRG method works even for asymmetric lattices, which we did in our paper. But for triad, I don't know. I think this is one of the limitations of the triad method, I think.
Okay. But there is many we can consider many variants of triad representation. So I recommend you to use the other representation of triad, like this.
Yeah, okay, maybe we can discuss this later, I think. Thank you so much.
Rich, you're holding the mic as if you want to ask one last question. I'm not hearing one. I think we should wrap up. Thank Daisuke and indeed all the lecturers one last time. Thank you.